Welcome back once again. My name is Mr. Chai. Today we're going to look at one of the CAIE A-level further maths question. Right, you can check the title here. This is a topics on vector. Okay, so it's vector topics that is found in further maths A-level. Okay, let's get started. Now, before that, you of course you have to read through the question itself. Here we are given two lines. The first line is labeled as L1, line number 1, passes through the point with the position vector given here, and then it's parallel to the vector here. The line number 2 passes through another position vector, but is parallel to another vector here. So since both of these direction vector for L1 and L2 are different, so therefore they are not parallel. Most probably they are sort of skewed in the three-dimensional space. Right? Now the point P is position on line L1, whereas Q is another point on L2. And then the conditions for this P and Q has to be perpendicular to both the line L1 and L2. In another word, it means PQ is the shortest distance between the two skewed line L1 and L2. Okay, now our task here is in any particular order, you can show that the magnitude of the distance PQ is 13 unit. And then we also need to find out the position vectors for P and Q. Okay, so if you are ready, let's try to apply some effective strategies to do this. Now, of course, a drawing of how the vector look like will be of much help to us at this point of time. Right? So let me just quickly sketch out the vector that we have. So I'm going to represent this as L1, for instance. Okay, this is L1. Now there is a position, there is a point sort of there is a position vector on this line here. So I might want to label it here, somewhere here. That is 8, 8, -7. For some of you who are not used to this vector form, the 8 on the first row represent the x coordinate. The second one is y coordinate, and then the third one is a z coordinate. So basically, this is a way to represent a point in three-dimensional space. Right? And then there's another point P somewhere lying on line L1 in this case, right? And then next I'm going to draw another line, which is something like this here. Okay, so from here we have this is L2. Okay, let me see. Maybe it's better if I draw it at the side here. It's easier to see. All right, now let me redraw that again. So this is line L1. There's a point 8, 8, -7. And then there is another point P lying on line L1. The next line is L2. There's also another position vector here, which is given as 7, -2, and a 4. And then another point Q, which is lying on the line L2 there. Now both L1 and L2 has a directions vector of, okay, I'll write this down. I will call this direction vector of L1 as, I think it's easier to just call it 1 there. Okay, so I just call this direction vector 1. So N1 is given as 4, 3, 0, whereas n2 is given as 4, 0, -1. So there's the direction vector there. Okay, now let me clean this up. Maybe there's a bit of confusion here later on. Okay, hold on. Just let me put this one down so that we know this is actually the point on the line. And then there's another one also is a point on the line here. Just let me clarify that. So this one is 7, -2, and 4. Okay, so these are points on the line there. And then P and Q is 90 degree. So PQ is perpendicular to both line L1 and L2 there, as indicated by the questions. Okay, so that is what we are having. All right. Now, if I were to answer this question based on the order number 1, number 2, then it's easier to solve it this way. Right? Okay. Let me see how am I going to solve number 1 directly in this case. Okay. Let's see here. Now, the first step would be here. Okay, just let me. The first step would be to obtain the perpendicular direction vector between L1 and L2 here. Between L1 and L2. So to get the direction vector that is perpendicular to both L1 and L2, I will need to get n equal to n1. Yep, I forgot to label this. Just let me put that down. This is a vector. So to get the directional vector that is perpendicular to both line L1 and L2, I will need to apply a vector product here, n2. Okay, so just let me finish calculating this first. So we have 4, 3, 0 here. We have 4, 0, -1. Okay, so let me try this out here. So the first one is -3. The second one is 4. And then the last one is -12 there. Right. Okay, so that will be my direction vector that is perpendicular to both line L1 and L2. Right, so basically I am done at this point. Okay, next I have these two position vector that I can consider here. Right, so let's label this as A and B then, so it's easier to work with. So this one is I would say OA. This one here is OB, so it's easier to see here. I'm going to rewrite here. So OA is given as 8, 8, -7. OB is given as 7, -2, 4 here. Now, therefore, the vector AB, position vector AB, will be given as 7, -2, 4. Subtract off with this, and then we have what we have here is -1, -10, and then 11. Right, now that will be our position vector AB in this case. Okay, and so now we have position vector AB. We have the directional vector, right? So maybe let me clean up this diagram so that um, we can get a better idea how we're going to deal with this. Right? Now this is the original sketch. I'm going to sketch another one here so that it's easier to work with here. I'll just do like this. So this is L1, this is L2. So we have A somewhere here, we have B somewhere here, and then we sort of have another um, a directional vector. So a directional vector which is given as n that we have worked out here, right? Okay, hold on, just let me get this straight. Okay, let me see whether I'm going to work with this or the other one. Okay, in this case, hold on, just let me check for a while. Okay, good. Hold on, just let me change this a bit. Okay, right. So we have a point AB given on the line L1, L2, and then we have a direction vector. This direction vector you can either draw it um, passing through B and so on and so forth because it's a vector. It's not fixed at one position. It just shows us the direction itself. So this is n, the direction vector that is perpendicular to line L1 and L2, and then we have AB here that we have already worked out, and then we are interested to uh, find out the shortest distance, which is actually a D here, the distance D. Hold on, we are interested to find the distance D here. So this is the distance D. Okay, this is a bit. Okay, hold on, just let me. This is the directional vector that is perpendicular to both L1 and L2. We are interested to find out the shortest distance between line 1 and line 2. Okay. And then we also know that there's an angle between this vector AB, position vector AB, and the vector, the directional vector that is perpendicular to L1 and L2. Right. So from just to recap, we're going to take out a bit of notes here. We know that n dot product itself, or scalar product, would actually yield this result. Okay, right. This is what we have. This first result, and then by looking at the this triangle here, this right-angled triangle, we can work out the shortest distance by using typical trigonometry. So we know that this distance is given by AB, the length of AB, cos theta. Cos theta. Oh yeah, I think I missed this out. The scalar product of n and AB is given as the magnitude, the product of magnitude, including the angle in between the vector AB and directional vector. Yeah, that's the part that I missed out. So you can see that here we have this section, which is actually the shortest distance that we're interested to obtain, which is D. So we can substitute this into here. So from here we get n dot AB is equivalent to, or equal to in this case, multiply with a D. And then we're interested to get the D itself, the shortest distance. Therefore, the shortest distance is given by the scalar product between the direction vector here and its magnitude. Okay, so in order not to produce any negative number, so I will include the absolute symbol here. Now that's how we get the shortest distance between L1 and L2, which is given as the length between PQ. So we can say that D is actually PQ, the length of PQ. Alright. So if you're ready, all you need to do is just substitute this n here. We have n. We have our AB. Right. So we're going to substitute it here. So if you're ready, we're going to work this out. Okay. Now before that, I will write down all the informations for our reference. Okay. So here, I'm going to erase all this. I'll just write down, since we know that this is a directional vector, this is given as -3, 4, and -12. Alright, so let me clean this up. Okay, right. And then we also found our position vector AB, so I'm going to write that down also. That is -1, -10, 11. Okay. Right. And then we know that the shortest distance between line L1 and L2 is given as the magnitude between PQ. That is given by this. Divided by its magnitude. Alright, so now I'm going to tabulate all this number so that we can work with this. Alright, so now the first step is to get the scalar product between the directional vector that is perpendicular to L1 and L2 with its position vector AB. So from here, we have -3, 4, -12, scalar product with AB, -10, and 11. So from here we have, let me see what we have here. -40, -37, so -37, and then -1212 is 13. 1212 is 132. So therefore we have hold on. So here we have -169. So the scalar product between n and AB is -169. And then the magnitude of this directional vector is given as so there's the magnitude there. Let me see, 16, 9, 25, 25, 144, 25, 169. So that should be a 13. Now, therefore, for PQ, it will be -169 magnitude divided by unit here. So that should be a 13 unit. Now, that's how we find the shortest distance between L1 and L2. Okay, I hope that is helpful. Okay. All right. Now next, how do we find the position vector of P and Q? P and Q. All right. Let me clean this up. Okay, so I'm going to clean up everything except for the diagram itself. Now the second approach is a little different. It's more algebra driven. Okay, so in this case, I will work out the equation for line 1. So equation for line 1 is given as, I will label this as equation for line 1 is given as 8, 8, negative 7 plus lambda, any parameters, including the direction itself. Okay, so that's line 1. Line 2, okay, maybe in line 2 I will write it down on the other side. So line 2, let's call this line 2 here. This is given as 7, negative 2, 4 plus mu, the direction, so 4, 0, negative 4. Now from here we can rewrite this as 8 plus 4 lambda. Second one is 8 plus 3 lambda. Next one is negative 7. Whereas the R2 is given as 7 plus 4 mu, negative 2, and then 4 minus mu here. So for this we can actually represent the position vector of P, because P is located on the line here. So we can say that this is actually position vector P, whereas this is position vector Q. And then we know that PQ is perpendicular to both the directions vector of L1 and direction vector for L2. So first of all, let's work out PQ, position vector for PQ. So position vector for PQ in this case would be 7 plus 4 mu, negative 2, 4 minus mu, minus 8 plus 4 lambda, 8 plus 3 lambda, negative 7. So from here we get a negative 1 plus 4 mu minus 4 lambda. And then here we have negative 10, negative 3 lambda. Here we will have 11 and then minus mu. And now that will be our position vector PQ. Okay, I hope that is clear. So the method that we're going to proceed next will be, we know that the position vector PQ is perpendicular to line L1, which means the scalar product between N1 and PQ must be 0, and PQ N2 must also be 0. Now that we're going to use this to form one sets of system of linear equation, and then we're going to solve for the mu and lambda. Alright, so I hope that is clear. Alright, so now I'm going to erase off, and then I'm going to use this result to work out the first one. Okay. So here, I hope this is clear. Just let me clear this up, so we don't need this anymore. All we need to have is the PQ dot with N1 would yield a 0. So which means this result here, scalar product with N1 would yield a 0. So that actually gives us negative 1 plus 4 mu minus 4 lambda, negative 10, negative 3 lambda, 11 negative mu, scalar product with 4, 3, 0 here. That will yield a 0. Okay, so just let me clean this up. Okay, we're going to work this out. So from here we have a 4, negative 1 plus 4 mu. Okay, I would say plus 3 here equal to 0. Okay. So from here we will have, let me see here, negative 34 here, we have 16 mu, we have a negative 16 lambda, that is negative 30, negative 34, negative 9 lambda equal to 0. Okay, so just let me simplify this a bit. We will have 16 mu minus 25 lambda is equal to 34 there. I think that's the furthest that we can go. So that will be our first equation. Now we're going to repeat this for PQ dot with N2, which will also yield 0. So from here we have negative 1 plus 4 mu minus 4 lambda, negative 10 minus 3 lambda, 11 minus mu, dot with the direction vectors for L2. So that's 4, 0, negative 1. That will be a 0. Okay, so from here we will be able to form. Just let me quickly finish this here. In this case, we have negative 4, 16 mu, 16 lambda minus 11 plus mu equal to 0. So from here we will have 17 mu minus 16 lambda equal to 15 here. That will be our second equation. Right. Is that correct? Yeah. Okay. So I think that is what we have at this point of time. Okay. I'm going to pause here for a while. Yeah, you can check one more time in case we make mistake on this. Okay. In case I make mistake on this. So let me see, 17, 16, maybe 15 there. All right. Okay. Okay, in this case, all right. Now just let me quickly solve this before. Let me solve this simultaneously. Sorry about this. Let's key this one in here. I think at this point I will erase off this section here. Let me use a bit of technology to help me with the calculation here. So I have 16, negative 25, 17, and then negative 16 here. I have another one, 34, and then 50. Okay. Alright, so this one. It's too small. Let me create the vector of this. Now I have the vector. Okay, so after solving these simultaneous equations, I found that my solution, okay, my solution is, just let me check one more time. The solution, of course, you can use matrix method, or you can use seek and destroy, or eliminations, or substitutions, or whatever method that fancy you to get the solutions to this simultaneous equation. So after solving this, you will find that your mu should be equal to -1, and then whereby the lambda should be equal to -2 here. Right? Now the solutions I will leave it to you to figure out, but that is what I have at this point. So that will be my unique solutions for mu and lambda here. Right. Now at this point, I'm ready to obtain the position vector for all p. Okay, so position vector for all p is basically 8, 8, -7 plus a lambda 4, 3, 0. Now since I have found my lambda, so I can substitute this all over here. That would actually yield 8, 8, -7. That will be -8, -6, and 0. And then eventually I have 0, a 2, and then that will be a -7. Now I'm going to do the same for all q also. Position vector for q. In this case, position vector for q will be so 7, -2, 4, plus with a mu. So mu is -1, so that is -4, 0, -1, and then that will yield a 3, -2, and then a 3. Now that will be my position vectors for p and q. Right. I hope that is clear. Now, of course, the last stage, I still need to verify whether my position vector p and q is correct. Right? So now to do that, I will need to use the informations that I have obtained from my first question, because the question state that the magnitude of length PQ is 13 units. So let me try to get the position vector for PQ first, based on the result that I have obtained. So in this case, it will be 3, -2, 3. Subtract over 0, 2, 7 here. Then that will yield a 3, -4, and then -4 here. Right, now the magnitude PQ is basically given by 3 squared plus -4 squared plus -4 squared square root. Right, so 9, 25, 16, 25, is it 25, 16, 25, 16, that will be 51. Did I get it right? So here 32. Right, so from here I get myself 41 unit. That is odd. Okay, just let me check if there's anything wrong here. So -4. Did I get anything wrong? 3, -2, 3. Did I get that right? There's 3. It's a 0. There's a 2. There is a -7. So Q minus that is a 3. Minus that is -4, and then there is a -4 there. So I need to have 14. Alright, hold on, just let me check for a while. Checking, alright, it's always good to check, as we are human beings, we make mistakes, alright. The same goal for me also. After checking, I found that this is where my errors are located. So the first one is because the the mu is -1, so I should have a -4, 0 here should be. So the error is actually here, this one here. So let me correct that. Oh, oops. Okay, I'll say oops. I did it again. Okay, so there should be a 1 instead. Then because it is a 1, so therefore that would yield a 5 now. So this one would yield a 5 now. So this is where my mistake. I made a remark here. And then this is a -7. Okay, I missed that out. This is a -7 here. and then this one here is a 5. Okay, that's a 5. Now we are getting the corrected value now, right? So 5 plus a 7 is 12 here. So therefore, I'm trying to rectify all my computation mistake here. So if you have a calculator, it will be safer. Okay. So there will be a 12, and then from here, we should be able, hopefully, pray very hard. Okay, so in this case, I will have a 9, 16, and then 144. So from here, 25 is 169. Square root of this will yield 13 unit. All right, so voila to us. Okay, all right. So checking, right, until you corrected all the mistake. And then in this case, we verify that both the vector method and then the algebraic method, with the help of a bit of vector, we are able to verify that the length of PQ is given as 13 units. All right, so that is the wrap for this problem. As usual, if you are interested with any video that I'm going to upload in the future, do subscribe and then press the notification bell. All right, thank you very much. See you again.